Know me, I'm Eric Unger. I'm the CTO and co-founder of Domonda, a SaaS startup where we try to revolutionize how small to medium companies and startups are managing their finances. So you can upload all your invoices, you can connect your bank accounts and credit cards and everything. And we basically combine all the data and you see what invoices you have to pay and what's your liquidity, and you can do, if you want to, the whole accounting thing and export that to your accountant, tax advisor, things like that. And we have been using Go for the backend since the beginning. And about myself, I'm a, let's say, veteran Go developer since 2010. I started before 1.0. And have fun building some infrastructure stuff and nice libraries that we are also using in production. And I'll show you our way how we do SQL databases and our interface for that. And so the question is, so why a new SQL package? Of course, there are many others out there, and of course we also started with what was out there. So in the beginning we used SQLX, so that has the same philosophy of what I'm presenting here. It's basically mapping database rows onto structs. So I think that's a basically natural mapping. Usually you have some kind of struct, and that's a database row. And we're using reflection to basically build queries and do stuff with those rows. And of course, if you want the max performance, you could use the native SQL interface from Go, but then you also write a lot of boilerplate code, and basically in the end, the latency of your query will always be magnitudes larger than basically the performance impact of using reflection.
Can you switch to your slides tab? Let me see it better on the screen here.
Okay, but I don't see what slide.
Yeah, we can follow along.
Okay. Okay. Yeah, so we started with SQLX and then started building on top of it because, of course, a library never does everything you want to. And then basically we saw that we kind of outgrow the whole thing, and it was also not very actively maintained, but we liked the basic abstraction here. And so what we then did, basically our developments, it's not like based on some big theoretical thing how you should do things. It's basically discovery of design patterns of code where you see, oh, that works nicely, and I don't have to write that much code for it. And so what works really nice is this one row is one struct, and also we're kind of power users of Postgres and SQL. We do some heavy lifting there, and we also like to write our queries mostly by hand and not have some ORM that has kind of this I'll reinvent SQL with the constructs of some programming language, which then never does exactly everything you need, especially if you're a power user. So we try to have that balance of you can do the simple things in a simple way, but you can do all the heavy lifting of SQL if you want to. And what I will show you later, also for us, regarding the architecture of our code base, the biggest discovery was how we basically do transactions, because of course you do a lot of transactions. If you do something serious and you want to reuse code and nest code within transactions and so on. And so we didn't find the real tools for that job, and I'll show you how we solve that using mainly the context argument that with like a modern Go code base you use anyways for cancellation for basically everything that's a web request, and we use that to also transport database connection and transaction data. But that's the last point here. So start with the basics, the simple things. So yeah, you configure a database connection. That shouldn't surprise you how that looks here. And yeah, we're using PQ as the database driver for Postgres. So it's a PQ connection that we are creating. And yeah, the important thing is how we map the struct fields, and that's configurable. So we have this struct field tag naming. Basically, it's an implementation of an interface, but that's the standard what you see here on screen, how we use it. You can do your own whatever, how you want to name your struct fields and how they map to a database column. Also have them automatically created with the untagged name func. So basically just convert everything to snake case. If that's the case for your code base, then basically you could just use that and not use any extra tags on struct fields. And so how does this look like? It's a little bit small here.
If you could try click you have a full screen in the StreamYard down in the corner. See if that helps you. In the corner here. Yep.
Yeah, that's nicer. So, so typically we annotate our struct fields with one configurable tag like db here, and that's then the column name. And what you can also see, there are some extra options like marking the private key, which can be used for some things where you have to know what the private key is, for instance, for updates and stuff like that. And below that, you see how to do a simple query a single row. That doesn't look that different from, say, the normal way how you scan single values. So you can see it with the user exists. That's basically kind of the same interface like the standard Go library. But what we have, of course, is this scan struct, which then uses reflection on the struct. And yeah, so where it gets a little bit more interesting is if you query more than one row. So what we discovered, typically what you have very often, that you also scan your table into a slice of structs. That's kind of the standard application. And for that, we have this scan struct slice. And you can also, if you just querying one column, use the scan slice into a slice. And nicest, if you don't want to use slices for some reason because it's very big, or you want to do it some other way, you can use a callback. And here it is, for each row call uses reflection on the past function, and it figures out that it takes a name and an email argument, and scans those arguments and passes it to the function. So that's very handy. Basically, you don't have to write any boilerplate code. You just write a matching function for your query. Of course, there's also a more generic way where you pass in, so that doesn't use as much reflection, might be a little bit faster, where you basically a function is called with the row scanner for every row that comes back from the result. And you can see here how that is used. And inserting rows, it's as simple as you could imagine. You can't make it any simpler than that. Just say insert struct. But maybe you don't want to insert all the fields of a struct, because you might have some default values like the ID or a created at timestamp, where your database has the default for those, and maybe you don't want to fill them in Go. just insert the data and then maybe query later what those defaults have been, what defaults have been set. And yeah, you can ignore columns. So the general rule here is that the queries always have to match your struct. So it's an error to have a query that, for instance, a query for like 3 columns and your struct has 4 fields and one can't be mapped. So that's an error. So of course you could do it that way. I've been thinking about that. Basically, you just don't set that one field that is not mapped. But usually that's a problem where you just overlooked something, where you expanded your struct and then forgot to update your query. And it's good that that query then fails because you see that your structs don't map exactly to your queries. And yeah, we also have an upsert. So basically, you all know the upsert. It inserts a row if it doesn't exist, or updates an existing one if it can be found. And here, that's an application where we use this private key tag that we're using here on the ID, but you can also have multiple private key columns, and basically it figures that out and yeah, inserts or updates the correct column given one struct. And then yeah, turned out we don't use that much. You can also do insert with a map of name value pairs, but yeah, mostly we are using structs for stuff like that. Now it gets really interesting. So this is how we do transactions. So the idea is basically that everything that runs in the transaction, or the code that runs the transaction code, is passed in as a function, and that function is called, and whatever happens in that function, if it panics, returns an error, whatever, the whole handling of rolling back the transaction and all this stuff is handled by this function. Basically, if you return an error from this transaction function, it's also returned by SQLDB transaction, and whenever you return an error, then that transaction is rolled back. And so that was the simple version, and where it gets really interesting and affects our whole design of our code base is in combination with the context. So yeah, you can basically add the context or a context to a connection. So that's kind of an anti-pattern in Go. Usually you shouldn't save a context, you should always pass it in, but it just makes it really nice, and you can make those constructs where you can change method calls and don't have variations on every method that is called context. So if you look at the original database or the standard database interface, so that for every function there's a context version and a non-context version. We don't have that. So it's always the method is doesn't take a context, but if you want to use a context for that query, you use a connection with context and then the query, and it's automatically passed along to that. And yeah, typically you would be using the context of some top-level function of a request handler and pass that along to the query, because of course your query should also be cancelled if the request gets cancelled or times out or whatever. And so yeah, if you put that all together, so we have a sub package, it's just called DB to make it short, and that sub package you can configure with a global parent database connection, and you can retrieve that using the dbcon. We try to make it short to type from a context. And what dbcon does with that context, it looks if the context itself has some connection, which can be a normal connection or can be a transaction connection, added as a value to it. If it doesn't have that, then it uses the basic global parent connection that has been configured, or else it uses that connection that's in the context. And that then allows something really interesting. So basically what we have, like a typical short function here that does a query. So it queries a user with a user ID, and that's all it does. It's very simple. So you could call that from outside the transaction, and it just uses the global database connection to query that user. But maybe you also want to reuse that function from within a transaction. So you have some code that does things in a transaction, and you just want to query a user, and you don't want to rewrite the whole code you see here within the transaction function. And basically you can reuse that via the context. So here's such an example. So it doesn't matter what it does, but it just does its stuff within the transaction. So you can see here, we have the get user or nil called within the transaction function. The transaction function gets a context, and that context in that case has basically the transaction connection, and the transaction will be used. And even if you have further DB transaction calls within a function that has been called within a transaction, it knows that it's already running in a transaction. And of course, you can start a new transaction in another transaction. You can do things like save points and so on, which we also support. But basically, that way of passing on transaction is for us that major feature that allows our software architecture to support basically those transactions, and you don't have to we can compose our code, and you don't have to worry about what I'm doing here. My function just queries a user, and it works within a transaction or outside of a transaction. And then, of course, there are helpers. You can do transaction options, knock yourself out there with the configuration, shortcuts for read-only. And if you just quickly want to replace a transaction, a DB transaction call with something that doesn't use a transaction to debug something, then we have this debug no transaction, which just wraps it like it would be transaction. So you don't have to basically rewrite your whole code just to disable or try out something without the transaction. And those are the most sophisticated things, which are kind of the power features, which also really enabled some really complex use cases for us. So if you're into databases, database transaction stuff, so serialized transactions and using save points and stuff like that. So I won't go into those things, but those are the things that if you need them, you really need them. And that's basically the short talk about our database interface. And if you want to have a look at some friends of Go SQLDB, we have a lot of other useful Go packages. So Go SQLDB uses Go types. We have a lot of types, especially like financial stuff, of course, for the Monda, but also nullable and non-nullable types you can use together with databases. We have our error package, Go errors, which is kind of our version of error wrapping with call stack and everything, which you might show also. And we have our own structured logger that creates JSON or whatever you want to use as a structure for the logs, really high performance. And you can check out our API if you want to.
Any questions?
I have a probably pretty basic question. about the context. What does the context look like? I'm not so familiar with it.
Okay, the context solves the basic problem that you want to cancel something that's running. And so typically you have a web server that handles a request and something happens to the request. The request could be canceled by the user, or there could be some general timeout on that request, whatever. And that your request handler calls some other long-running code, like does a big database query. And basically you want to tell that other code that basically from top down there has been a cancellation. So your user, because your export of all your data from the website took too long, pressed the cancel button, or there was some network timeout or whatever, and you don't want to have basically a query going on for another hour for a request that was already canceled like 50 minutes ago.
But can I also look at it as some kind of map which sets in Java it would be a thread log or something where I could set the transaction the first time I call a database.
Yeah. So it's basically, you can see it like a map for key value pairs that you can add to that. So it has two functions. So one is cancelability. So you can set timeouts or another cancel function where you can just say that context is canceled. And the other thing is you can attach data to the context, and that's just key value. And that's how we inject the database or transaction.
So if I have like two database actions I want to do, and I call the first one, with the context, it probably would create, or I have an overall spanning transaction over that. And then that first one could create an inner transaction, and parallelly, I could give the context to another action or do another action on that, which already picks, also creates a transaction, and they check that there is a parent transaction in the context and build on that.
Yeah, so you don't use the context for synchronizing between threads and stuff like that. It has basically just, it's something you pass down per convention to every function usually, and you have this signal of basically the context of everything you're doing has been canceled. For some reason, everything you're doing can be canceled. So typically on the lowest level, if you write a function that gets a context and you don't call another function that then also checks the context, usually what you do is check, is the context canceled and does it have an error? And then you return that error. So basically you early out as early as possible when you see that the context of the thing you're doing has been canceled. And the other thing is, it's also used not only for those cancellation messages or signals or whatever you want to call it. It can, of course, also be used to transport some data. And usually what you have is you have like a request ID and a logged in user ID, and you can all put that into a context. And you can use it for tracing, or you can use it for like nesting transactions. So typically you would have request handler, the request already from Go in the standard library has a context, and that context gets canceled automatically when that request gets on network level canceled. And you pass on that context to all the function you are calling from your handler function. And then basically every function earlies out with an error if it sees that this was canceled. And also, if you start within that context transaction, and you have other code that's running, database code that's running within the transaction, it also, of course, gets that context and sees, oh, I'm running in a transaction, so I'm not starting another transaction or do whatever I need if I'm in a transaction. Of course, you can also, I haven't shown that, you can also check that you're in a transaction, stuff like that, but usually you just want to query the database and not worry about in the function that you're writing, if am I in a transaction or not.
More questions?
Yeah. You mentioned you're pretty heavy Postgres power user. What kind of sophisticated stuff are you using from Postgres specifically?
So we are using a lot of Postgres functions because we are using PostgreFile for our front end. So PostgreFile is a tool where you can create your whole GraphQL API from a public Postgres schema. And basically that leads to a design where you do a lot of queries directly from the front end, not going through Go code at all. And then, of course, if you're doing that kind of thing, then basically you can extend your GraphQL API with custom SQL, PL/SQL, whatever function you want to use. And that leads to, let's say, more SQL code and SQL function than usual.
So you're using procedural languages for storing procedures.
Yeah.
All right. Other things like, SQL stuff that's not so standard beyond Postgres, like composite types or trigram extensions or something.
No, I mean the trickiest parts is things like locking stuff. Yeah. And here we have those things I've shown here. So these serialized transactions and save points and stuff like that. And so we have then some logs that live in Go code and some logs that live in SQL land, and it all has to be synchronized, and that really can get tricky.
I can also add that we're also using these advisory logs, and it allows us to use the database as a synchronization point between multiple services. So what we can do is we can elevate the database's concurrency patterns to synchronize code across all programs that are doing something at the same time. And we also have built a job worker, and on top of that we use all the concurrency things like select for updates and all those nitty-gritty stuff, so that all those workers don't race with each other. So
yeah, and that's also one of the reasons why we want to use for SQL, because simple things like select for update, that might be the next best. URM might have missed that. You can't do that or whatever.
Yeah, I mean, we also did something similar, because you can do it specifically pretty well with Postgres because it has a pretty sophisticated deadlock detection logic. We have other projects where we unfortunately use MySQL, and we just move the login to Redis or something because it's sort of easily locked down the whole database if you have 20 concurrent things happening at the same time. So,
You ask questions before we go? Yeah.
Yeah. You said that you were exposing the whole database somehow to the front end, right?
No, a schema. So we have a public schema, and of course we have other schemas which are private.
But how do you also make sure that this is private and this is public, so that not everything gets exposed to the front end?
So we have row level security, and basically that's how we ensure that basically you can't have something, a query where a user, for instance, doesn't. So row level security, a user doesn't have even access to a row of something. Even if you try to query it, you just won't get the result. That's built into Postgres, and we're using that. And that's also directly connected with PostgreFile. And we're using the user login to identify the user and have the security level on that. So a user can only query basically his own, for instance, invoices in our case.
So sort of like anonymous and then also user role, and then right? You might have anonymous role as well, which can fetch the public schema, and then the user which can fetch it.
Yeah, right. So it depends, and you can configure that, but basically a logged in user can see more than a public user could see.
Thank you.
Cool. There's no more questions, so we can continue here locally with more questions afterwards, of course. Then a big applause. Thanks a lot.
As a bonus, I could show the call stacks.
Yes, let's do it. Is it fine if we're still live? Or should
So probably not, because it's our private code
Then
base. so-
thanks everyone watching live. The recording will also be available. Bye bye.